Hi, and welcome back to our online discussion this week. For the first problem, we want to show that for any parallelogram ABCD, we have that AD squared, which is one of the diagonals, plus CB squared, the square length of the other diagonal, is equal to 2 times the sum of the squares of the length of one side plus the length of the other side, which is AB and AC. So how are we going to solve this problem using vectors? So first of all, we can situate our parallelogram in the plane. Right, we can situate our parallelogram in R2. What we can do is that we can make these line segments that we care about into vectors, right? So we can set AB to be our vector x. We can set AC to be our vector y. Great, so set the segment AB to be x and set segment AC to be y. And then how can we express our two diagonals, AD and BC, in terms of these two vectors? So notice that by the rule of vector addition, the way to add our two vectors x and y is tip to tail, right? So what is x plus y? It means I need to move this y. If it starts here, I need to make it start here, and then I need to make this draw this thing that is parallel to y, right? So this is what we call tip to tail. So this the resulting length here is exactly x plus y. And how do we calculate x minus y? We again do tip to tail. So we put the tail of y here, but we reverse the direction. Right? And so the resulting vector here is x minus y. But this is just the same length as this thing here, right? So x minus y is indeed our other diagonal. So now we can notice that to prove this proposition, this is equivalent to showing the following statement, that the length of x plus y squared plus the length of x minus y squared is equal to 2 times length of x squared plus length of y squared. Great. So let's start with the left side, see what that is. So recall that for any vector v, the length of v, or the length square of v, is equal to v dot v. So x plus y squared is equal to x plus y dot x plus y. And we can use the rules of dot product, and so it distributes across the plus, so we get x dot x plus y dot y plus 2 times x dot y. Similarly, we can compute x minus y length squared. This is x minus y dot x minus y. This is equal to x dot x plus y dot y, but here we have a minus 2x dot y. And therefore, if we add these two equations together, we have x plus y norm squared plus x minus y norm squared equals to 2 times x dot x plus y dot y. And here the 2 x dot y and minus 2x dot y cancel. So this is what we have. But then x dot x is exactly x norm squared, and y dot y is exactly y norm squared. And this is indeed what we're looking at on the right-hand side. So this completes the proof.